Hello, this is Rohan, and today we are going to check out how to prove you know a secret without revealing what it is from up and atom and up, something like that. So it's a fascinating title, and let's just start the video and just learn more about it, the maths behind it, and yeah, here we go.
Stream for sponsoring this episode. Get access to my streaming video service, Nebula, when you sign up for Curiosity Stream using the link in the description. Hello, welcome to Up and Atom. I'm Jade. What if I told you that there's a mathematical technique where you can prove that you're right without even telling anyone what it is that you're right about? Sounds impossible, don't you think? How can I possibly prove to you that a secret I know is true without telling you the secret? Like this. We have a jar of candy clouds. I reach in and choose two. I swear that they're different colors, but I don't want you to know what the colors are. How can I prove that they're different colors without showing them to you or telling you what the colors are? Feel free to pause the video and think about this if you'd like. Alright, I put the candy clouds under 2 cups. When I close my eyes, you either switch the places of the cups or leave them. Then I look at what's under the cups and tell you correctly whether you switched them. After I guess correctly once, you aren't going to be very convinced, right? My chances of guessing whether you switched them were 50-50 or 1 in 2. So we do it again. Because the statement I'm proving really is true, the candy clouds really are different colors, I'm right again. Now the chances of this being a fluke are 1 in 4. We can keep going as long as you want. If you want to have a less than 1% chance that I'm lying to you, we'd only have to repeat this 7 times. If we repeated the swap or don't swap routine 100 times, the chances of me answering correctly every time without knowing the candy clouds were different colors is less than 7.89 times 10 to the power of minus 31. Practically impossible. This number isn't actually 0, so I haven't given a mathematical proof that I can't be lying. But if you aren't satisfied, we can keep going until the odds that I'm lying are smaller than any non-zero number you choose. Then we say that I have proven that I know a true secret, and you have verified that I know a true secret. We didn't just find this on a piece of paper somewhere, we interacted to construct this proof. Our Candy Cloud game satisfies all the requirements of what's called a zero-knowledge proof. A special type of interactive proof in which one party demonstrates they know something without giving away any information. In our example, I was the prover and you were the verifier. I proved that I had the secret by answering all the questions correctly, and you verified it by knowing whether you had switched the cups and therefore knowing what the answer should have been, swapped or not. Now let's think about how we did this. To know that we'd be able to construct a zero-knowledge proof, we both had to be honest. I was telling the truth. I really did know the secret that the candy clouds were different colors. We both followed the protocol. You told the truth about whether you had switched the cups each time, and I correctly told you whether or not you did it too. This property of a zero-knowledge proof is called completeness. Whenever the prover really has a secret and both parties follow the protocol, the verifier will agree that the prover really does know the secret. That covers the idea that we want to be able to prove things that are true. Soundness is what guarantees that we can't prove anything false. In practice, this means we can get the chance that I'm lying to be as small as we want. I wouldn't have been able to correctly say whether you'd switch the cups each time unless my claim that the candy clouds were different colors was true. And finally, you have no more knowledge at the end than you had at the beginning. You don't know the colors of the candy clouds or which one is which. You only verified what I told you, that they were different colors. This is called zero knowledge. Not only can the verifier not cheat and learn more than what they're supposed to, but an eavesdropper hearing swapped, didn't, swapped, didn't, and so on, wouldn't be able to tell whether we'd made the whole thing up or whether we'd really verified something because only you know whether you switched the cups. Therefore, only we know that my answers were correct. So to qualify, a zero-knowledge proof needs to satisfy all 3 of those conditions: completeness, soundness, and zero knowledge. If you find the existence of zero-knowledge proofs hard to believe, you're not alone. The early reviewers of the groundbreaking paper must not have believed they were possible either, because the paper was rejected multiple times. When it finally was accepted, its authors, Shafi Goldwasser and Silvio Micali, were awarded the A.M. Turing Award by the Association for Computing Machinery, generally considered the highest award in computer science, sometimes called the Nobel Prize of Computer Science. Okay, so this is pretty cool, but can we actually use it for anything? Just 6 or 7 years ago, there were no real-world applications of zero-knowledge proofs, but that has changed with the rising popularity of cryptocurrency. For the very first cryptocurrency, Bitcoin, the inventor essentially had to make a choice between trust and privacy. In order for people to believe they weren't being swindled, there needed to be a permanent, unalterable public record of every Bitcoin transaction. This was called the blockchain. The issue is if that one person used Bitcoin to pay for something like cancer treatment, that transaction is public. Anyone can now see that user Jane Bit paid for cancer treatment. That's a pretty big compromise of privacy. Enter zero-knowledge proofs. For some cryptocurrency, people don't have to make such public.
Okay, that's it. That's all. We need to watch the video for to understand what is a zero knowledge proof. So basically, all we need is that the thing is, there are instances where you're doing something and someone else needs to verify, and for that verification, you might need to give the information in a public domain. Now, the example given is a blockchain. Blockchain is basically a public ledger now, which other parties verify, and so for verification they need to know everything what you have done, and that's why you have to reveal everything, and that's then only they can verify. And if they verify in that way, then all that record is public and anyone can see. That's a breach of privacy. To stop that, to prevent that, you can have the same trust and the same confidence of a blockchain by using zero knowledge proof. Zero knowledge proof is like you are not giving the incorrect information, like by the way of analogy she proved that you're not telling which color is which. You're just telling I have two different colors, and they are telling you, they are checking whether asking you a question. We are swapping the cups, just tell us it is true or not, and they keep on doing this such that the probability of you lying is very very less, and hence the transaction is verified, and you have not shared any information other than whether the cups were shared or not. We have not gone to the mathematical lingo, but I think that is, if you want to watch that, you can watch a video. But we have got the sense that what is zero knowledge proof. You are not giving any information like which color is which. You're not giving the minute details. You're just giving the layering information that the colors are different. And the verifier is also not revealing any information, because if any third party comes and hacks the system and see what is written in blockchain, it is already public. But if it was inside a bank or something, if someone sees, they will not see any information, because the verifier only checks whether it is swapped or not. Or what does swap and unswap means is irrelevant. It has a meaning only to the person who is verifying. So the zero knowledge proof is that you get the confirmation that it is true. She proves, verifier proves that it is correct, and both of us does not share any knowledge, and also the third party does not share knowledge. So this is a very beautiful mathematical thing. I think she will explain further in the video what the mathematical layerings are, the equations, and how it works. And if you were interested, you can go and watch it. But this was an amazing video. Zero knowledge proof. You can prove something, that something is true, without revealing what it is, and the other party will know that is true or not without checking what is inside. That's a fascinating thing mathematics can do. It can give rise to such an insight. And definitely the thing about that is application. Obviously, in science and mathematics, the application might not be immediate, but that's not the problem. If something is profound, something is amazing, it will find its application sooner or later. So it found its application in the blockchain, and there might be many more places it might have its application. We just need to look forward and but just be hopeful. That's an amazing video. Till next time, take care.